Our goal is to find the minimum time it takes for all these given n nodes to receive the signal. So if we take an look at this example, so starting from 2, what is the minimum time it takes to cover all these nodes? So we can see that from 2 to 4 it takes 2, from 2 to 1 it takes 1. So the minimum time to cover all these nodes, it's 2. Why? Because within 2 time we can cover all these nodes, because 1 will be inside 2, it's also included. So it boils down to the fact that we just need to get the maximum time of it, and since the constraints of these weights is positive, we can solve this problem by Dijkstra's algorithm. So let's jump into coding. First, let's define our graph, which will have the node to its list of integer value. So this will be our graph. Because for integer, we'll be holding the time of destination and time it takes to get there. So let's go over this time that we have. And for first entry, what is it? It actually says it here, u, that is the source. So source is times 0. What about the second entry right here? And that is the target node. So target is our time 1. What about the third one? That is the time. So that's the third one. So let's put these things in our graph. And for source, we will put let's put time node, just to differentiate the names in here. So for source node, we are giving the value of, construct new array list and add this new integer value with, can give the time it takes. So time node to target node. Okay, now we have defined our graph. Now let's Dijkstra's algorithm is very similar to BFS, except for the fact that it utilizes priority queue. So let's define our priority queue, which takes the integer array, because we will hold our time and the given node, so nodes that we are at, so with this weight. So priority queue, and this is our min heap. So for min heap, and then this is an array. So for the first value that we will be saving, that will be our time. So we'll be ordering it by its time, and we can just give first time when we are at this given k, which is 2. It's just 0, the time it takes to get to itself. And another thing we need to define is our visited set, where we need to keep track if we have seen this one or not. Otherwise we might fall into just in a cycle of just like seeing the nodes. Now we can actually, like I was saying, it's like it boils down to get the maximum value out of here. So we need to get the time where we can do the processing. Let's define this one, because like we'll be doing processing while PQ is not empty. And here we'll do some type of processing, and then utilizing the maximum time, reassigning it to this one, and in the end we'll just return delay. Another thing to note that it needs to see all these nodes. If there is some type of there is no connection between some nodes, we can actually return -1. So let's make sure that, so when we visit every single of them, this the size of this visited set has to be equal to the given vertices. So given vertices, seeing, that's how we know it's like if we have visited everything. So if it equals to, then we can return our delay. If it's not, then just -1. Okay, now let's do our processing in here. And we can remove from our queue, and this will give us what? This will give us integer array. This is the current that we're looking at, and first value, it is the time. So current time 0, and second value, it's the node, so current node is 1. Now if we have seen this node, then let's just skip it, because like no need to process it. Only time if we don't we haven't seen this current node, then process it. So we can take care of that really quick by saying checking our visited set contains this current node. If it does contain, then just continue. So if it doesn't, then let's go and process it. So we can I mean, if it doesn't, first thing first, let's add this current node to our visited set, and let's calculate our delay. So for the previous delay that we had it, and this current time. So every time you will be keeping the maximum time of it. And let's go inside our graph. So prior to this one, let's see if we actually have the value for given current node. So if it doesn't, then just return us empty array list. And what is the value that this map is returning? It's returning a list of lists, which is our neighbors, because we will be traversing it and seeing these neighbors here. So for each neighbor in our neighbors, what was the first value in here? Time node. Okay, so time, it's neighbor time. This is the first value in our neighbor. Neighbor node, that's the second value. Okay, now we need to just add it to our priority queue. So our priority queue contains integer array, so new integer array. For given neighbor node, we just need to update its time, because neighbor time will be the time, because like we are doing the path, traversal path. So for the current time that we are looking at, we need to add the neighbor time to it. So, and then this is for the neighbor node that we are looking at. Because like we're updating our path, and when we are looking at this 2, when we get to 3, what is the time it takes? 1, right? So how long it takes from 3 to 4? So because like this one was 1, so 1 plus this 1, it takes 2. So this is the calculation it's doing in here. So that's about it. Let's run our code. Oh, so because we are saving it as an array, so 0 to k. New 0 to k. Because we're making a new array entry, so let's run our code. Perfect. So time complexity. What is the time complexity? Time complexity in here, we are seeing every single nodes in here, and for each of them we are making an operation of removing it and adding it in here. So priority queues, adding and removing it, it's log of n, where n is all those values in its priority queue. And for seeing every single edges and vertices in the neighbors, is O of, you can say E, where E all those edges. So the overall time complexity is O E times log n, you can say that. And for space complexity, we are using extra space, where we have this graph, and we're also having this priority queue. And then overall, we can say this is O of n, where n is all the vertices in this graph.